principle, the methods that we demonstrated then are applicable to a set of any number of such ODEs. So in principle, if you had n unknown functions and n coupled ODEs, describing those solutions, if there is a simultaneous solution to that system of equations, and each equation is of this type, which is susceptible to the Laplace transform method, so linear with constant coefficients, and maybe whose the term in each equation which is independent of any of the unknown functions, as long as that function has a Laplace transform, in principle then that method should allow you to obtain the solution to the system, if such a solution exists. What we're going to go on to now is still sticking with the same idea. And so in the tutorials, either some of you have tutorial today, others have tutorial on Monday, we can still be working on examples of those pairs of ODEs. Okay? Should still be practicing that. In general, if you look through the past exam papers, I think almost every year you're asked to, one of the questions asks you to obtain a solution to an ODE using the Laplace transform method. So it really is a key skill to be very practiced at and be very confident in doing. Okay? So if you look through the past examination papers, you'll see plenty of examples of those. So we're now going to widen out the scope of the enterprise now by bringing in some more functions, okay, which we mightn't have met before. So we're going to do that now, and the two types of function we're going to talk about, the Dirac delta function and the Heaviside step function. These are just named after the two mathematicians or physicists who lend their names to these functions. Now there's an example example 2.10 here, which features, well, it doesn't necessarily look like an ODE because it's featuring an integral in it. There's a derivative and an integral, so you'd maybe call this an integral equation or that. But it's equivalent to an ODE because you've got this unknown function I. So this I of t is the current flowing at time t through this circuit. We've got a derivative of I of t, and we've also got an integral of I of t here. Now we're not going to focus too closely on this. We're not doing electrical engineering or that. That's not our focus here. But it's just to illustrate one case where we might need to be able to handle step functions. Okay? Because in such a circuit might behave differently, whether it's driven by perhaps an alternating current or a direct current. So electrical power is typically transferred in these two different forms. And alternating current is where the direction of travel of the current is changing many, many times a second. I think the electricity that comes to our sockets is about 60 hertz, is it? Or 240 hertz? If you look at the back of some piece of electrical equipment, it'll say, but some kind of high number of hertz per second. So the direction of travel of the current is reversing direction many, many times a second. That's called alternating current. The other type of current, which typically comes from, say, a battery or something, is direct current, where the current is only flowing in one direction. So the graphs of that kind of current, to just kind of schematically might appear as they do there in figures 2.2 or 2.3. So the current might be switched on for only a certain period of time. So most of the time the current is switched off. So the graph of the current function is just 0. But in some time interval, the current might be switched on, and an alternating current might have a signal like this, and a direct current might just have a set level of the current. So what we'd like to do is have some way of representing signals that are switched on and switched off. Okay? So this is what our Heaviside step function enables us to do. Okay. So what we want here is some way, a mathematical way, a nice mathematical way to describe signals that are turned on and turned off. Signals or functions, signals or functions that are turned on and turned off at various times. And it turns out, in order to do this, all the one kind of key building block that we need is just a basic notion of a switch. To have a mathematical description of a switch. Now this turns out to be very straightforward to do. Okay? We've got a variable t. We think of t as like a time-like variable. And we think of this function, which for all negative values of t is equal to 0, and at t equals 0, the function switches on. It then changes to a value 1. But this is the graph of the Heaviside step function. It's named after Heaviside, who was a British engineer, I believe. Heaviside step function, typically denoted with the letter h. And the definition of this function, it's a function that's defined by a couple of cases, depending on the argument. If t is less than 0, it's set to have the value 0. And if t is greater than or equal to 0, it is set to have the value 1. Okay, so that's the definition 2.2 from page 52 there. Okay, so it's just something which is switched off for half of its life of negative values of t. We can take it to be a function that's defined on the whole real line. It's switched off for half the time, and then at t equals 1, it switches on. It turns out that in order to describe signals that turn on and off at various times, we don't need a whole suite of switching functions. Really, we can do everything that we want just by using this one function. We can move or change the location. We can move the time of switching. What if we wanted a signal not to switch on at time 0, but maybe to switch on at some other time, a, say? How would I mathematically describe this kind of switch, which is switched off? I mean, it's difficult to draw, but you can think of the graph of the function as being 0 here. I mean, it's difficult to draw because I've also drawn the axis there, but so you can imagine the graph just being 0 everywhere, but then at time a it switches on. Well, I don't need a whole new function to do that. That can be performed by translating the argument of h of t. So this is the graph of h of t minus a. If you think about that, h of t minus a, according to the definition, just repeating the definition, this should be 0 when t minus a is strictly less than 0, and 1 when t minus a is greater than or equal to 0. But of course, that's equivalent to saying t strictly less than a, and t greater than or equal to a. So it is indeed, that is indeed the graph we see. Function 0 everywhere up to the point t equals a, and then at the moment t equals a, it suddenly switches on, takes the value 1. Okay. So the function h taking the value 0 is equivalent, interpreted as being switched off. Taking the value 1 is switched on. So we're just going to run with this function, do a few things with it, and then eventually consider what its Laplace transform might be. Because that will enable us then to solve differential equations that feature this function. So let's look at example 2.11. So look at number 1 there. It says if A is strictly less than B, so we assume A is strictly less than B, what are the various values taken on by this function g? And let's draw a graph of g. Well, consider g of t. Now this is defined as the difference h of t minus a minus h of t minus b. Now what is that going to be? Well, let's think about it in terms of the various cases for the argument t. And see, if a is strictly less than b, that kind of suggests that the graph of it, I can draw this here, so here's my a, here's my b. Well, that kind of splits the domain up into 3 different regions, doesn't it? Less than a, between a and b, and greater than b. Well, you see, if t is less than a, if you look back at the definition up here, at the top, h of t minus a, and think of that as h of t minus b, well, for values of t less than a, t is going to be less than a and less than b, okay, because a is to the left of b. So for values of t over here, both functions are taking the value 0. So it's overall, it's 0 minus 0, so it's going to be 0. For values of t between a and b, when you're here, well, see, once you go past t equals a, this function on the left switches on. Yeah, that takes the value 1. The second function is still switched off at value 0, because if t is in here, t is still less than b. So overall, you've got 1 minus 0. So you've only got the value 1. 1 for values of t between a and b. But once you go past b, once you go beyond b, then both of the functions are switched on. So you've got 1 minus 1. So you're back to 0 again. You'll be back at 0 forevermore. So I haven't stated whether a and b are bigger than or less than 0 or that, so there's no, so we just got the vertical axis somewhere. We don't know where the origin is, but this function is going to be 0, then taking the value 1 between a and b, and then back to 0 again. So it's going to have that kind of graph. So now we've been able to create a signal which is switched off all the time, except for a certain defined time period, and it's switched on between A and B. Okay, so what you need to appreciate here is how that difference of Heavisides, h of t minus a minus h of t minus b, how that produces this signal. Switched off, and between a and b it's switched on, taking the value 1. Then once you go beyond b again, because it's 1 minus 1, both signals are switched on, but you're subtracting them, so you're back to the value 0. Okay, any queries based on that at the moment? We could look at number 2. So number 2 just changes this a little bit. It says, well, what's the effect of adding in a function, some non-trivial function now, 1 plus the cosine of t. What's the effect of multiplying that by h of t minus a minus h of t minus b? Well, if you just consider the function 1 plus cosine of t, cosine of t is a smooth signal that's varying between plus and minus 1. So when you add 1 to it, it lifts it all up by 1 unit, so it would be a smooth signal varying between 2 and 0. And when t is equal to 0, cosine of t is 1. So it's going to be something like this kind of a, without being too precise about it, that's what the graph is going to look like, isn't it? It'll be the typical graph of the cosine function that's just lifted up the page by the unit 1. That's the effect of adding this 1. But it's, so that would be the graph of this function. We didn't have the other factor there. So what's the effect of multiplying it by this factor? Well, in effect, you're multiplying it by this function here, which is this graph. So on most of the domain, you're multiplying it by 0. But between a and b, you're multiplying it by 1. So multiplying it by 0 will get rid of this signal. And multiplying it by 1 between a and b will leave the signal alone. So the graph of this function f, I could even just bring down my a and b, just kind of put it against, but wherever you put the a and b, it doesn't really matter. I just want to indicate what's happening. So the red function, that's maybe not that clear. But just for emphasis, I'm putting a thick red line here. So this is the graph of the function f. It's the same as this function 1 plus cosine of t between a and b, but outside of a and b, it's back to 0. Because you're multiplying the value of this function in the square brackets 0 everywhere outside of the interval a and b. So this red graph is the graph of the function f of t. So this combination of Heavisides is in effect a switch that we can use to switch it to take some signal, which maybe gives a non-trivial signal over the whole of the domain, but hitting it with a difference of Heavisides has the effect of only switching it on in a certain interval and leaving it switched off everywhere else. Okay? So let's look at question, well, yeah, there's a further little question. We can extend this up to even more kind of cases. So here you've just got two types of behavior, either switched off or taking on the value of this signal 1 plus cosine of t. We look at number 3. We're considering this function here, vt, which is 0 for t less than 0, t for t between 0 and 2, and then 2 for t greater than or equal to 2. So draw a graph of v and find a definition for v, not utilizing different cases. It's up on the screen. Instead, utilizing a combination of Heavisides. So we want to draw a graph of v and then give an expression for v in terms of Heaviside step functions. So we can approach this. So we're going to have values around 2, between 0 and 2. Let's make this 1, 2, 3, so you can see things, what's happening here. Well, the graph of this function v, you see for every value of t less than 0, it takes the value 0. So we just got a function which has got value 0 down here. It's equal to 0 for every value of negative t. But then between 0 and 2, it suddenly takes the value t. So that's going to be this linear function of slope 1. Then for every value of t bigger than 2, it's back to being a constant function. This time it's just the constant 2. So then forevermore it will be stuck with the value of 2. That's what the graph of this function is. Maybe more appropriate to call that a ramp function. Instead of a step function, the Heaviside is like a step, something that takes an instantaneous step up in value. Maybe you'd call this a ramp function. It's changing smoothly from the value 0 up to the value 2. Smoothly and evenly, gradient 1 up to the value 2. You see, we can think of this as the sum of 3 different functions. V1, V2, and V3, to give the 3 different types of behavior. So we can think of V being the sum of these 3 functions, where V1 of t is equal to 0. Well, it's kind of a bit silly, but 0 for all t and r. Well, so we really don't need to think of that. V2 of t, which is equal to t for 1 less than equal to t less than 2, and 0 otherwise. And then V3 of t, which is equal to 2 for t greater than or equal to 2 and 0 otherwise. So each of these 3 functions, V1, V2, V3, can be realized using Heaviside step functions. Actually, I needn't have bothered including the function V1 because it just has 0 behavior. So it's not going to, I'm talking about a sum, the V1 just as well mightn't be there. It's only contributing 0 to the sum. So I was thinking a bit too generally there. So V2 we can think of as t times a difference of Heavisides. H of t minus 1 minus h of t minus 2. Just as in the previous example. When you have h of t minus a minus h of t minus b, that switches a signal on and off between a and b. There, the signal I want is t, but I only want it between 1 and 2. And V3, I want to be the signal 2, but I want to only switch it on when I get past the point 2. So that's 2 times h of t minus 2. So then V of t, I can express as V2 plus V3. This is going to be t times h of t minus 1 minus h of t minus 2 plus 2 times h of t minus 2. So I can get this now. I could, if I want to tidy this up and express it as t times h of t minus 1 plus 2 minus t times h of t minus 2. So that's the kind of expression for V that this little exercise was asking. Find a definition for V, not utilizing the different cases construction. So it's equal to this if T is this, equal to that if T is that, equal to the other thing if T is another property. But just a single expression for it using a combination of Heaviside functions, which is this kind of expression. I mean, the different cases are still there, but it's just they're bundled up in this standard way into the definition of this Heaviside step function. We haven't magically gotten rid of this different cases behavior. We've just kind of expressed it using this in this standard kind of way, using this one single device of a Heaviside step function. So that's the Heaviside step function. I'm going to look at it in a moment. Now we'll look at its Laplace transform. The other type of function we want to introduce is, well, strictly speaking, it's not a function in the ordinary sense of a real value function that we're used to talking about. It's perhaps more properly called a distribution. It's maybe something like a probability distribution, something that can be integrated. It's defined to have an integral 1, actually, over the whole domain. But where it's going to arise is representing a sudden impulse, or kind of instantaneous, momentary impulse in a system. So it's got this definition that it's 0 everywhere, except at the point 0 where it has the value infinity. Or we can also look at delta of t minus a, again shifting the argument, just like we did with the Heaviside function. So we can look at delta of t minus a. So this will be the function which is equal to 0 everywhere, except for at this one point a, where we kind of think of it as taking the value infinity. This impulse of sudden delivery of energy to a system. And you maybe can draw a diagram of it by, well, it's not really a graph of it, but you can represent it diagrammatically as a kind of a graph of a function which is 0 everywhere, and there's just a single spike located at the point A, pointing upwards with an arrow indicating it's got infinite value, so to speak. So it's a bit of a hazy kind of a loosely or non-rigorously defined thing for us at the moment. You can make it more precise when you talk about it kind of as an object that can be integrated. And it's the integral of this over the whole domain is defined to have integral 1. Okay, but what we'd like to start to do then is, so these are functions which can help to describe various situations and which can crop up in the differential equations that we want to look at. So if we're going to use our method of Laplace transforms to solve these, we will need to know how to take Laplace transforms of these functions. Okay. So if you go to page 55 there, we've got theorem 2.4, which shows us the Laplace transform of the Heaviside step function. So I think we'll maybe do this in the next results now, but it'll probably be next week before I start to show you some examples of solving differential equations featuring these. Okay, so this theorem says basically that the Laplace transform of the Heaviside step function h of t minus a is e to the minus as over s. Okay, so this doesn't look that intimidating. We can try and tackle this using the original definition of the Laplace transform. So we'll just do it directly. We'll leap straight in. I think we'll assume that this point, yeah, it's not written in there. What we'll do is we'll assume that a is bigger than 0. T is generally representing some kind of time-like variable. So we normally model something beginning at time 0 and model it on into future time. So we'll take it that this interesting point A is some point in the positive domain. Well, what's the definition of the Laplace transform? It's the integral of e to the minus st dt. And the other factor in here is the function that you're taking the Laplace transform of. And we're taking the Laplace transform of h of t minus a. Right, that's the definition. Somehow we've got to bring that to e to the minus as over s. At the moment, it perhaps looks a bit challenging. We've got this strange new function h, and we've got to take an integral of it, multiplied by an exponential. So when described like that, that could be hard, integrating a strange new function. But remember, the Heaviside, it's not really that strange. It's very boring, in fact. It's not completely boring. Completely boring would just be a constant function. Okay, it's a little bit more interesting, but it just takes two different constant values. So this h of t, or this h of t minus a, like down here, it's either 0 or it's 1. So actually integrating it shouldn't be that hard. We'll either be integrating it as having the value 0 or having the value 1. All we have to be careful about is where it changes. So it changes from having the value 0 to having the value 1 at this point a. So what's the consequence of that for this? Well, see, we can split this integral up as the integral from 0 to a plus the rest of the integral from a onwards. Okay, all we've done there is just use that principle that integrating over a large integral, you can split it up as the integral over the first bit. Just do that integral first, and then integrate over the rest of the integral. Okay, so that's just a basic property of integration. You can split an integral up over a large integral, split it up into subintegrals. So we go 0 to a first. Remember, we're assuming a is some point beyond 0. So we can go from 0 to a and then go from a on to infinity. But now you see, between 0 and a, h is very simple. It's just equal to 0. So you're integrating 0, so actually you get nothing from that. In terms of working towards an answer, it's good. We can just forget about that. It's not giving us anything. Here, on this interval, when t is between a and infinity, h of t minus a, well, it's just equal to the value 1. So this integral becomes simpler. Really, we're just integrating the exponential, e to the minus st dt. So that looks eminently doable. It's e to the minus st over minus s, evaluated at, sorry, not a, not 0, but a and infinity. And again, assuming the real part of s is a positive number, the limit of the integral, sorry, the limit of this exponential e to the minus st as t goes to infinity. As we explained before, as long as the real part of s is bigger than 0, that will converge to 0. So you'll only be left with the evaluation here at t equals a. So this will just be equal to minus e to the minus sa over minus s, providing the real part of s is positive. And that's the answer we need. E to the minus sa over s, isn't it? So the two minus signs cancel. And we do indeed get e to the minus as over s, as required. Okay, so that's a proof of that result. So we can take the Laplace transform of the Heaviside function without too much trouble. Let me look at the next result. So the next result deals again. You see, that will allow us to take the transform of a Heaviside on its own. But the question is, well, you see, like in this example here, remember when we treated this signal v? We didn't end up with the Heaviside on its own. We ended up with the Heavisides multiplied by other functions of t. And the previous example, suggestive example, this one, so we're not just considering Heavisides, but we're considering them multiplied by other known functions. So we're going to encounter the Heaviside playing a role like that, the Heaviside function multiplied by some other function. So this next property will allow us to deal with situations like that. So this next theorem deals with the Laplace transform of f of t minus a times h of t minus a. So the two functions, the Heaviside function and the other known function f, they're set up or they're arranged in a similar way. They're both evaluated at the same type of shifted argument. So they're both evaluated at t minus a. Okay? So a is some shift. And we're assuming that this function little f is a function that we know about. So we know that the Laplace transform of little f exists, the original function f of t exists, and that's known to us as some transform function capital F of s. If that's the case, then this theorem 2.5 tells us what the Laplace transform of this new function is, so the new function f of t minus a times h of t minus a, and it gives it to us as a kind of a shifted version of f, but now shifting the values of f, evaluated at s, shifting them by multiplying them by that exponential e to the minus as. So this again is just an exercise in integration, doing theorem 2.5, and it will turn out that really theorem 2.5 is all we're going to need. That should enable us to deal with the Heaviside functions as they arise in the differential equations that we're going to look at. So, yeah, 10 minutes, that's enough time. So theorem 2.5 is the proof of this. Again, we'll jump into it directly. By definition, this is the integral from 0 to infinity, e to the minus st times f of t minus a, h of t minus a times dt. But now we know what we're going for. We're going for this result, e to the minus as f of s. Just about fit it in here. We're trying to get that this is e to the minus as times capital F of s. Well, what is that? That's e to the minus as times, by definition, capital F is the transform of the original function little f. Okay, now it's looking a lot more approachable. You just got to get that integral at the top, an integral of an exponential, there's f. We've got to make it this thing here. Okay, the exponential is, well, one bit of the exponential is moved outside. You've got f inside the integral. They're looking kind of similar, these two. So we've got to bridge that gap somehow. Now again, this Heaviside here, remember, it's just switched on and off. And it changes from being switched off at the point A. Previous to A, so for t between 0 and A, remember this is the value 0. So this means we only need to consider the integral from A to infinity, e to the minus st times f of t minus a dt. Okay, so the other bit is just equal to 0. So it's not there. Now this is, so the kind of consideration here is this integral is nearly the same as this one. It's an integral of an exponential times f dt. This is integral of an exponential times f dt. But there's a few subtle differences. This integral goes from a to infinity, whereas this integral down here goes from 0 to infinity. In this one, the function f is evaluated at t minus a. This one, the function f is evaluated at t. There's a few subtle differences. But we can make a bridge between those differences by using a substitution. So we'll use the substitution. So instead of t minus a, we're going to introduce a new variable u. So u is t minus a. We're going to change the variable of integration. Now, this is only just a fixed constant shift, so the two differentials, du and dt, are actually the same. Okay? It's just a fixed constant difference between u and t. So we're going to change this integral to one involving u. Now, when t, we have to change the limits as well. Well, you see the upper limit, as t goes to infinity, what's u doing? Well, u is just a steps behind t. So as t goes to infinity, so does u. As t goes to infinity, u follows behind, the distance a behind, but it gets to infinity too. T begins at a in this integral. So that means u is going to begin at 0. This is going to be an integral du. So if we change the variable to u, it becomes an integral from 0 to infinity. This is good because this is matching this one. F of t minus a, well, I'm replacing t minus a with u, so this becomes f of u. But in the exponential, I've got e to the minus s times t. And when I get rid of the t and replace it by u, well, I have to replace it by u plus a. Okay? Because t is equal to u plus a. So that's the change of variable. Successfully changed the variable away from t. But now this integral is looking quite a bit more like this integral. From 0 to infinity. This is from 0 to infinity. Got some kind of exponential, I've got some kind of exponential. I've got the function f of u. Well, here's the function f of t. It's the same, it's behaving the same in terms of the integral. Now something new has been introduced to this exponential bit. It's e to the minus su minus sa. Well, I can split that apart there. I've got e to the minus sa multiplied by e to the minus su, f of u du. That's just using properties of indices. E to the minus su minus sa in the second to last integral. So in that one, I just split the two exponentials apart. But then I notice that this factor here, as far as the integral is concerned, integrating with respect to u, this factor is just a plain old constant. It's just some fixed value, isn't it? The integral is changing u, sending u from 0 to infinity, but this e to the minus sa always has the same fixed value across the whole integral. So it acts just as if it were the number 5 sitting there. So that can pass outside the integral. It's just a fixed constant as far as the integral is concerned. So this goes to e to the minus sa, integral 0 to infinity, e to the minus su, f of u du. Now, have I bridged the gap there? Well, it kind of looks like I haven't, because this thing is talking about u, and this is talking about t. Remember, like in all of mathematics, these letters we use, they're just arbitrary choices. They don't have any inherent meaning, right? What is this object here? This is an integral of this function times this function. And the argument u goes across every real value from 0 to infinity. This integral is exactly the same. It's integrating this function times this function. The argument of the function goes through every real number from 0 to infinity. Just by tradition, by accident, most of the time we talk about integrals dt, but it means nothing. The t means nothing. What we're talking about is integrating these functions evaluated at these real numbers. So this integral is exactly the same as this. The fact that this is quoted in terms of u is neither here nor there. It could be quoted in terms of anything. It's exactly the same integral as this one here. And it's exactly the same factor in the front, e to the minus sa. Okay? So these are exactly the same. Don't get put off or confused by the choice that one of them is expressed naming the real number u, the other one is naming the real number t. They're both real numbers. They're both going, what we do need to have the same, we do need to insist is the same, is we're going across the same range of real numbers, from 0 to infinity. And that's the same in both cases. And the functions are just evaluated at those real numbers in exactly the same. So those are the same. So we get the desired result. We get all the way down to e to the minus as times the transform of f as required. See, I need to practice my presentation a bit because I ended up with a gap. I shouldn't have had that gap. Although the gap allows me to write that in, so maybe it's perfect. I don't know. So that's a proof of how the Heaviside function behaves in terms of the Laplace transform, both on its own, theorem 2.4, and when it occurs multiplied by another function. Okay, so next time we'll look at applying these results to some ODEs which feature these signals that are switched on and switched off at various times using the Heaviside function. It's like essentially you can take this now and run with it. You can start on the exercises in 2.4 even. But for the tutorials, you'll see there's a new set of exercises there at 2.3, and just some more preparatory exercises with the Heaviside step function.